Okay, this one will get slightly more interesting. We have a, so consider a sequence of logical statements. And let's call the statements A1, A2, A3, and so on. So we have one statement for each whole number greater than 1, greater or equal to 1. Okay, so after a while you might have A200, but you always have one more. So we have an infinite sequence of logical statements. Sure. So these are all true. For all numbers n greater than or equal to 1, so whole numbers. Okay, so this saying this is the same as saying A of 1 is true, and A of n implies A of n plus 1 for all n greater than or equal to 1. Doesn't think about it for yourself for a while, that'd be great, and I'm about to continue on to discuss this problem further. So maybe to make this simpler, instead of considering an infinite sequence of logical statements, so maybe we can consider a finite sequence. Consider just 3 statements. That's even simpler still. Okay, and then we can move to 5 when we get to it. So 3 statements, A1, A2, A3. And so what is this statement saying now? If we were to show the analogous thing for 3 statements, well, the left-hand side would say, is saying that A1, A2, and A3 are all true. Okay, that's all the left-hand side is saying. So what's the right-hand side saying? So the right-hand side saying is A1 is true. Okay, so that corresponds to that part, which is good. But it's also saying that it's also saying that A1 implies A2 is true, and A2 implies A3 is true, and it's also saying A3 implies A4 is true, A4 implies A5, but since we only have 3 statements, let's just say that those are no longer included in the right hand side. Okay, so can you see that if all A1, A2, and A3 are true, then it's clear that A1 is true, A1 implies A2, and A2 implies A3. So so when all 3 are true, it's certainly the case the right hand side is true. But what if the right hand side is true? Does that mean the left hand side is true? So if the right hand side is true, it means A1 is true. Okay. And then A1 implies A2, and A2 implies A3. So can you see how if A1 implies A2 is true, and A1 is true, then A2 can't be false, because if A2 was false, then A1 implies A2 would be false. That's the only way an implication can be false. So therefore A2 must be true. So looking at right hand side, we see that A1 equals true and A1 implies A2 equals true means A2 must be true. Okay. And actually for the same reasoning, A3 must be true. And we can actually even use the result we showed earlier, because A1 implies A2 and A2 implies A3 implies, that A1 implies A3. So A1 implies A3 by previous exercise, and therefore for the same reasoning A3 is true. And actually if you notice what's happened, if we change 3 statements to 4 statements or 5 statements, we're really just doing longer and longer chains of arrows to establish all of the statements are true. Okay, but that doesn't necessarily give us what to do for the original problem. Okay, and I want to maybe come back to the original problem at another time. Okay, so can you see how a simpler version of the original problem is to apply this ABC logic over and over again to get to prove that some finite sequence of statements is true. The problem now is to show this for all the statements, so for the whole sequence of statements. And we might think it's a problem because we only show it for so many, and if we keep going, how do we know we'll get all of them? There's infinitely many of them, so maybe we'll never finish and we'll always leave some statements out. But the nice thing about the logic is when you prove something for all n, it's the same as proving it in practice for an arbitrary n. And after you fix this arbitrary n in your proof, the number of statements you're proving will essentially be fixed. So let's have a look at this. So it's clear that if the left-hand side is true, that is all of AN, all the statements AN are true, then the right-hand side must be true. Because A1 is one of the statements, it's true. And AN will imply AN plus 1 because all of AN and AN plus 1 are all true. So true implies true is a true statement. So the right-hand side is true given the left-hand side is true. So let's just show if the right-hand side is true, then the left-hand side must be true. So suppose A1 is true and AN implies AN plus 1 for all n whole numbers greater than or equal to 1. And we want to show for all n whole numbers greater than or equal to 1. So if we want to show something for all n greater than or equal to 1, the logic will be to show it for an arbitrary fixed n greater than or equal to 1. So let n greater than or equal to 1 be an arbitrary whole number. And now that we've fixed it, we only want to we just need to prove that a and one statement is true. So we need to show that for this n, so can you see how this is different? Because this particular n, even though we don't know what it is, we know that there's only so many numbers below it. So we know from previous considerations that A1, A2 is true, A1 is true, A3 is true. So we definitely know that, we saw that explicitly, but we also saw the argument carried on to A4 and actually to any fixed number. So it carried on to this n, whatever it was. Okay, so we have actually a lot of things that are true, and we actually only needed that am was true. Oh, and these previous considerations used this assumption. Using this assumption. So in particular, an is true. Okay, so that's the logic behind what's called a mathematical induction. And essentially, you're just proving a sequence of statements are true by linking them all together. So the statements have some sort of counting structure that the numbers have. And the trick or subtlety is in converting this infinite string of statements into just a finite string of statements in the proof.